So first, who are we? I'm Jan Jaeger. I'm a sales director at eChart, responsible for binary analysis solution called EOS Reverse. We are located in the Bordeaux area in France, but as you can hear, we are not limited to only French people. We have a lot of international customers, and we have built tools now for both hardware and software security. Beyond offering security testing, we have the mission to simultaneously transfer knowledge and expertise, rather not talk about tools, but platforms that we are offering to our customers. So our mission is to empower our clients, making them stronger and self-reliant, both now and in the future. And what I would like to say always, and I get back at the end of this webinar, we are the dash between the know and the how. So diving into the eChart solutions, basically we have two solutions. One is for hardware security, that is our chip testing unit. We have solutions for side channel analysis and for fault injection and failure analysis. And we have a strong partnership with Alphanov that provides the lasers that we are using ourselves and also provide our customers with the lasers from Alphanov. With our EOS Reverse platform on the right-hand side, that's our system security unit that is basically using the EOS Reverse platform. We have a binary security analysis platform. Doing binary security analysis is the best way to perform security tests, and why I will get to back later in the presentation. It's also possible, by the way, to integrate bespoke tools in our open and flexible platform. So we are not limited to the tools in EOS Reverse, but if you're using some other tools yourselves, you can also integrate it in our platform. Looking at EOS Reverse, we basically are talking today about our fault injection capabilities, but we also have other reverse engineering techniques in the platform, and we also support all kinds of architectures like RISC-V, ARM, or Intel. So the first question, what is fault injection? Like I said, I noticed that some viewers do not have the semiconductor background or maybe even electronics background. So I want to dive in a little bit on the fault injection and what the effects are on firmware. So the first question, what is fault injection? Well, basically, what fault injection is deliberately introducing errors to a system to introduce faults. And how do we introduce those faults? Basically, a system has like operation conditions, like the temperature and all other conditions that are used to operate, or what are ideal to operate in. And what we try to do is try to manipulate the execution of the code that is executed in the hardware. Usually the errors that are introduced are unexpected hardware errors, and that could potentially unlock undesirable code paths. And I'll demonstrate that a bit later in this webinar. These code paths are rarely tested, and why is that? Mostly developers are focused on testing their functionality of the things that programmed. But of course, just like the airbag that you see here exploding at the crash test dummy, it is something that you are normally not testing because you have to wreck the car to do a testing for the airbag. And I think the same thing is here at firmware testing, where developers do not really test code paths that are unusual, or at least it doesn't happen a lot. So there are special testing tools for that, and today we dive into one of those. So how to inject faults in hardware? Like I said, chips are designed to operate under predefined circumstances. So what we try to, or what a hacker tries to do, is to see what happens if those predefined circumstances are changed, or if they are not ideal for the operating of the hardware. So what happens if you push the limits of those circumstances? And what happens, I can already tell you, glitching is happening. So what kind of circumstances are we talking about using or operating a chip? One, of course, the easiest one is the temperature. So I would say room temperature would be the ideal temperature to operate a chip. But of course, what happens if you are putting the chip in a refrigerator, or maybe even cooling it more, or maybe heating it up? That could possibly have a glitching effect. Another one is the power glitch. So power glitching is actually using or playing with the voltage, and I'm going to demonstrate or show you a little bit in the next slide how that would work. Power glitching is, I think, one of the easier things to perform if you want to do some volt injection. Another one is clock glitching, where you can slow down or speed up the clock of the device. So basically, what you want to do is create some errors because instructions are performed too fast or too slow, and that would also perform or would result in error behavior. And other things are electromagnetic radiation and laser volt injection that you can do, and therefore you need a little bit more sophisticated equipment, but it's quite easy to do if you have the right equipment for it. So let's dive into this a little bit more. So here I have a simple example of voltage glitching. You can see on the left-hand side a little bit of how that works. You just connect the pins of a board, of a PCB, and you try to play with the voltage. And what you want to do is see at what time you want a glitch. So the glitch delay, that's the number one here in the picture. So what time do you want the glitch? That could be just after booting, or that could be at a certain moment in time that when you are aware that there is some kind of check performed that you want to glitch. You can also see how long you want to glitch. So how long do you want, let's say, to drop the voltage of a chip? And of course, you can also look at what would be the drop in the voltage. So how many volts do you want to drop it? And of course, all these conditions are necessary to do a glitch at a certain time, where you can somehow try to fool the chip. And of course, the zeros are 0 volt, and the ones, the bits, are let's say 3 volts. What happens if you drop the voltage for a short period of time? What kind of behavior would there be? Of course, you want to have the behavior that the processor is maybe a little bit confused, and that is the target that you want as a hacker to attack on firmware. So this is like a visualization about what an attack would look like, what normally you would do in a research lab. So in yellow, you see where there is a reset of the chip, or maybe it is even fused out if you're using voltage glitching, or if there is some kind of protection. So yellow is not what you want. The green is where nothing happens. So basically, it is just ignored, the glitching. And of course, in the red, that's where it gets interesting, because that's the area where you know that you have a success chance of hacking into the device, or at least establishing some kind of behavior that it was not supposed to do. Fault injection, it's not science fiction. It happens a lot. We have seen it a lot in well, recently a Tesla that was unlocked with all the software options worth of for $50,000. But there are also other hacks in the past on DJI drones, on Bitcoin wallets, not limited, by the way, only to Trezor, but also to other manufacturers in the market. Cisco's IP secure phone, and a little bit more recently Starlink, that was also hacked. So you can use the Starlink system for free instead of paying for it. And of course, that's not all. In different ways, it is damaging for the devices and for the manufacturer of the devices. But in some phase, in some instances more than others, as you can imagine. And of course, the sun is also doing its own EMFI because of the radiation on satellites. Satellites need also to be protected against solar flares, because that can also affect the behavior of the software running in the satellite. So this was about hardware fault injection. It was a clear explanation. I see a raised hand. Mr. Hassan, maybe we can do this after the webinar, because I want to continue my presentation, and we are collecting all the questions from the chat. So if you can put your question in the chat, or my colleague can already answer, or we can answer it after the webinar.
Yes, for sure. It was after the discussion. It was for after the discussion. Sure.
Okay. Yeah. Thank you. Okay, let's move on to the next slide. So what are the effects on firmware, the fault injection? You have understood now that it is possible to tamper with the hardware and to inject faults by changing the operating conditions of the hardware. But firmware is software, and why is it affected by this? And basically, what you can say is that it is quite easy to tamper with if you have access to the device, and most of the time it is possible. And you can actually change the behavior of the firmware by attacking the hardware. And there are a few things that I can tell about it here in this slide. So one of the things that you can do is making it skip instructions. So if you inject a fault at a certain time when an instruction is executed, you can influence the instruction, or even you can let it skip the instruction. And of course, if that is just a check if you are authorized to do things, or maybe it's like a cryptography check, then if you have the right access rights, or if you want, if you are in the boot sequence and you can skip the boot check, if the firmware is really the firmware that is supposed to run, then you can do a lot of things. And skipping of instructions is the most common used technique with firmware fault injection attacks. And specifically the compare or branch skip instructions can result in unwanted code paths. And I think in this in the demonstration at the end of the webinar, we also are going to dive in this situation, the compare instruction, for instance, to check for keys if they are matching or not. Another one is incorrect data fetch, so bit flips, so to say. And of course, bit flips can result in all kinds of different things. But basically, if the security critical data is corrupted in this way, that affects the software for sure, and may fall back the software in a less secure state. And of course, that is a very unwanted effect. And of course, you can also cause jumps in the instructions, maybe by tampering with a program counter, or even exchange or achieve multiple instruction skips, which result in wrong code execution, and that might give all kinds of unwanted effects. So what are the targets and the objectives if you are attacking the firmware? That's of course a very good question to ask. And why? Well, fault injection is a physical attack on the logic, and the goal is to bypass, of course, things like secure boot mechanisms, but also maybe extract a secret key, or maybe bypass cryptographic signature validations of firmware binaries. I mean, if you are in for instance, a bootloader, and you have effectively made sure that the cryptographic signature is the validation is not performed, because you are glitching at the moment that validation is performed. You could lose you could upload your own firmware in the device, and of course that is not what you want. Furthermore, circumventing memory readout protection to expose sensitive data that resides within microcontroller's internal flash memory is something that you could achieve with fault injection, or re-enabling hardware debug functionality of systems that maybe have been disabled, the debug functionality on production, but you can switch it back on using fault injection. And of course, bypassing input validation of data, and especially crossing trust boundaries. I think that's something that you are all familiar with trusted execution environments, secure elements. You don't want people to get access in the so to say trust zone of the trusted execution environment without the right privileges. So these are the things that you can achieve with fault injection, or not limited by to these, but at this moment these are I think the 5 most common targets and objectives that hackers have to attack your firmware. So testing the firmware, I have a few considerations here that I want to at least tell you before getting into the details about testing the firmware. Code bases only grow bigger in size and complexity. And I mean, that has really grown over the last years. And I have a few examples later on in this slide about what has happened the last, let's say, 20 years. But what you need to think about is that immature code has one vulnerability each 1,000 lines of code, usually. And if you do a manual evaluation, what I would not suggest, but if you want to do it, then you can review about 1,000 lines of code a day. So, of course, sometimes it is done maybe for certifications, but you can understand that this does not scale, because we nowadays have systems with more than 100 million lines of code, and that is not really doable by manual evaluation. So basically, they just have to put to check some code that they can do in a few days, but at least it is not a code check that is completing. That's checking the complete code base. So the conclusion from that consideration is that automation is needed, and automation and good tooling is needed, preferably in a CI/CD pipeline. So if you're developing firmware, you want to do automated checks every time you commit a new piece of code, and maybe you want to perform some previous tests that you have done already and see if the new code did not introduce new vulnerabilities. So it is important to have automated security checks in your process, and preferably that should be in a CI/CD pipeline. And another consideration I want to give you is what are we asking from developers? I mean, developers are focused on functionality, and developers are not security specialists. So maybe we have to help them by automating checks and give them feedback in the right way, so they can also do some mitigation and learn from their mistakes. And firmware, of course, because it is so close to the hardware, it either enables or mitigates attacks that exploit hardware weaknesses. So there is the dependency on the hardware. So here is like a short overview of the growth in code over the last 20 years. So as you can see, the smart card solutions only were about 100,000 lines of code. Smart meters in 2010 already went over 1 million. And you can see the growth with iPhones or mobile phones, and Teslas nowadays with more than 100 million lines of code. And with AI nowadays, who knows how much code base will grow or maybe even shrink. I mean, I don't really foresee where this is going in the upcoming years. So testing the firmware, basically there are some tools to provide that provide static checks and dynamic checks. Looking at the static checks, the big disadvantage of doing static code checks, so testing in the C source code, is the false positives. And the false positives, it's like a false alarm, but with a false alarm you still have to check if it's really a false alarm or not, and you even also explain, or triage as it is called in hospitals, that it really is a false alarm, and you have to document it as well, so you have seen it but you have not acted on it. So that's a lot of work, because with static code checks I think about 90% is false alarm. And that means that it's a lot more work than you benefit from it. But now and then, of course, there are some things found with static code checks. Then we also have dynamic checks. So those are checks done at runtime. The hardware is needed for that, or at least some kind of emulation, but I get to that later on. And of course, you have to compile the code before you can run it in the runtime environment. And to do the dynamic checks, we have our platform EOS-Reverse, which is a binary security analysis platform. And what we do is run the firmware on an emulated hardware environment. So it is not necessary to have the hardware available. We can emulate it. We have built our own based on QEMU system that we have enhanced, and where we can run the hardware on, or the firmware on, and do it on the architecture that it is meant to be to run on. So the hardware is not needed, and as you can imagine, this is also important if you want to include things in the CI/CD pipeline, that you have the complete environment at hand, and you can run it without needing to apply all kinds of things, or install hardware, or even let the hardware run somewhere. This is really flexible and good to do. And of course, when you want to make the shift to the left, so the shift to the left is the offloading some of the work from security analysts towards developers. So make developers also smarter on security issues. That is something, if you want to achieve that, then you need to run it in an emulated environment, because then you can do automated code checks and automated dynamic analysis checks in the CI/CD pipeline. So looking at countermeasures, what can we do to prevent fault injection from being successful and changing the behavior of the firmware? That is, of course, a question that many people ask themselves, and there are a few ways. So there are hardware countermeasures like sensors or redundancy, obfuscation, or even if, let's say, if you are doing voltage glitching, you can fuse it out, or any other protections. These are things that I do not get into in this webinar, but if you're interested in that, you can contact our chip security colleagues that have more knowledge about this subject. I'm looking more at the mitigation patterns in the source code. So basically what you can do, if you have most source code is written in C, so what you can do is have some mitigation patterns in place, like complex large Hamming distance constants. So you need to flip or change a lot of bits to achieve a different behavior. So that's one of the ways. Double checks is another one where you can make it harder to attack the branch conditions. Check the same conditions twice. It's TOC2, time of use is a different approach, and you can use that in the pattern. Loop integrity checks are a way to make sure that important loops are executed, and you can check afterwards, if a certain index has the same value and that value is only reached if you are going through that loop. So that's one of the things that you can use to mitigate. Of course, there's also default error handling or default failure, where if anything happens, that the return value is always a failure and never a success. So you cannot bypass any authorization or any checks that are done in the software. And lastly, there you can use a flow monitor, where you use a counter, and that is incremented every time an instruction is performed. And if that is performed, then at the end of the run, it needs to reach a certain value. And if it did not reach that value, like say value is 10 and it is 9, then you know that that there was an instruction skip, and you can take mitigating actions on that. So looking at those countermeasures, of course, you can do it in the source code, in the C source code, but after source code, there is the compiler that is compiling to the binary. And of course, the compiler needs to compile for the right architecture. There are all kinds of compiler settings that you can use. And of course, sometimes if you do redundancy, or maybe you're using some of the checks here in your mitigation patterns, the compiler is smart enough to see that things are done twice and can be optimized. And then, of course, you're back to square one, because the mitigation that you have put in place is undone by the compiler optimization. So you have to keep that in mind. So now let's move into the binary security analysis. The reason I was talking about binary security analysis is, like I said, in the source code, there is a compiler that needs to be perfectly set to compile for the code that is used in production. So you want to have a reflection of the code that is used in production, and you need to be sure that it is compiled with the right compiler. So source code checks can be quite inaccurate. And of course, there's the compiling step, which makes it not the best way to go. Another option is to do it in the hardware description language. So that is, of course, the most closest to the reality, to the real world, but it's really complex to implement, because you need a lot of knowledge of the HDL or the RTL to be able to get to the good result. And of course, many chips are bought off the shelf, let's say from ARM, the IP. And if the chip is bought off the shelf, then most of the time you do not have access to the RTL of the chip. And that makes it also not an option to use it in daily testing. So there we go. We are at the binary code level, where we think you have the trade-off between accuracy and complexity is the best, and the optimal balance between accuracy and complexity is the best. And of course, it is a reflection of the real life code, because it is the binary, so it is already the production code, or at least compiled with the right compiler settings. And that's a real reflection of what you want to test. And of course, with our platform, we can also do some reverse engineering on it, which makes it even better to test with a binary analysis. So having said that, I hope I got the message across that that binary analysis is, in our opinion, the best way to test for firmware resilience. And I want to dive now into the EOS Reverse platform that accommodates this. So I'm not going to explain everything that is in the platform. As you can see, there's quite a bit of functionality in the platform to facilitate any binary security analysis that you want to do. We zoom in today on the fault injection test, but you can see there's also static analysis, stress testing, and all kinds of collaboration features to help you set up the test with your colleagues and also hand over work without losing precious time. And the user interface of our platform is based on Jupyter Labs notebooks, which are a mix of documentation and Python scripts that you can execute. And of course, we believe that this is the best way to perform or replay a test. And also, if you do it 1 year later, then you still have the right documentation and scripts and settings, configurations, data sets at hand that you use the first time. And that makes it very efficient to also do regression testing. So looking at fault injection testing, how do we do that with our platform? There are a few things to think about. First one is, what architecture do you want to load and execute the binary on? For that, we have a number of architectures available. Our most used is ARM architecture in embedded software, but we also have Intel and RISC-V. The next step is to select a fault campaign, including a fault model. So you need to think of what to target, like registers, memory, or instructions that you want to target with your attack. Where to fault, so the program counter or an instruction trigger that you want to tamper with. And you need to think about fault timing, so when to fault, and maybe also the instruction range that you want to target. And of course, how to fault. So choose the fault model like instruction skip or bit flip or some kind of timing and duration of the attack. So these are all variables that you can set in our fault injection testing. And I think in the demo, we will dive into that a bit more, and you can see how that would work in practice. So setting up the fault injection test, of course, here you see a screenshot of our of one of our Jupyter notebooks for that explains the fault injection on firmware. So there are a few steps that you have to take. First, the architecture, like I said before, ARM, RISC-V, or Intel. But if there is another, if you have an architecture that has QEMU emulation, then I think it would also be possible with some tailoring to do that as well. Then you look into the firmware, because there are a few options. You can emulate the complete execution of the firmware, but that's not really effective, because then you also emulate all kinds of instructions that are not really sensitive to fault injection. So no checks for authorization or stuff like that. So it's good to analyze the firmware first and see what are the parts in the code that are sensitive for fault injection, or at least if a fault is injected, that could be damaging, or changing the behavior would be damaging of the firmware. So, and that of course would also result in a faster execution of the test, because you do not have to execute the complete source code or the complete code of the firmware. Another thing that you need to think about is looking at the hardware. Do you also want to have an emulation of all the references to other hardware that it uses? But because it could be that there is a special AES check or a hardware check that you want to emulate, or maybe replace it with a software implementation, or maybe you want to stop some addresses that are accessed in the firmware, but that you do not have available in the emulation. So those are considerations you need to think about. Do I want to stop, or am I going to implement the hardware references that are done outside the emulation architecture? And step 3 is, of course, executing the fault injection. So we are going to demonstrate that in the demo in a bit. And the last step, not to be overlooked, of course, you want to analyze where did the behavior change and what did it result in, and can I repeat it, or is it just a one-time thing? It's more coincidental. So you need to analyze the behavior, and we do that by recording traces and see if there is a deviation in the execution of the firmware. So analyzing after the test, for that we have functionality in our platform called timeless analysis, where we can capture an execution trace. And with the timeless analysis, we can travel forward and backward in time. And we have implemented this functionality to be able to see the state of the complete system at any moment in time. So basically, the real-time constraint is removed, and with the bar in the bottom, you can shift to left or right and to move forward like just with an old-fashioned cassette player. You can just go back and forward and see the state of the registers and the data and memory at a certain point in time, and that makes it very easy to see what happened during execution, why the behavior was changed during an injected fault. Another option is to do a taint analysis, and that is looking at the data to see what is the effect issue if the data is changed, and where is the data used in the execution. So it's a very useful method of seeing what is the propagation of data effect on the execution of the firmware. So emulation frameworks, I think I mentioned that already a bit. So we have for x86 and x64 systems, the Intel, we have full VM emulation. We also have for ARM32 and ARM64 architectures emulation, and we have in general QEMU and Unicorn support. So if your architecture is not here, maybe there is already a version that can be emulated, and that we can at least run a fault injection test on that. So that brings me to the demo that Mathieu has prepared.
Hello everyone, we're going to look at a typical workflow of running a fault injection campaign using ES-Reverse against the firmware. Before we talk about how we can do that and what the results look like, we need to talk a bit about the why. So the fault injections campaign usually refer to applying certain types of hardware level faults to an execution, which might unlock certain code paths which are completely unexpected from the developer point of view. For instance, one of the variable might see its value change for no particular reason, and obviously that's not something that the developer is taking into account. However, this is really hard to test because if you need to test that on the hardware, you need a bench with certain things like a laser or an EM probe, and you need very specific skills to be able to do that effectively, and then expensive oscilloscopes. So yeah, the iteration loop between detecting a potential issue and actually changing the firmware is going to be very long. However, there are certain code patterns which are by default going to be sensitive to fault injection, whether or not it's easy to trigger them with actual fault injection hardware. So the idea of ES-Reverse is to provide tools to either the analyst or even the developer themselves in order to make that iteration loop much smaller and much less expensive, because we are only running on software and emulation. Okay, so now that we know why running a fault injection campaign is interesting, let's look at the example we're going to work with during the demo. We will look at a firmware which has a security feature in the form of a signature comparison. The idea is that at the boot of the firmware, it computes its signature and then compare it against a known signature. If the signatures are similar, it continues with booting. Otherwise, signatures are different, it refuses to boot because it means the firmware has been tampered with. And the comparison function is here. It just compares like 8 byte. Again, this is just an example. And because we want to make it simpler for us to see what's going on, instead of running that function at boot, we're going to simply make a binding on the command line of the firmware in order to be able to run that. The binding looks like that. So it takes two signatures and it compares them. And if they are equal, it prints access granted. Otherwise, it prints access denied. So that's going to make it simpler for us to see what's going on, but you get the idea. It's supposed to be running at boot. If we look at the firmware in action, this is what we have here. So our firmware is running there. We're not doing any injection yet. We're just looking at the behavior that we have. We have our compare v1, and if we run it against two different signatures, we have an access denied as expected. And of course, if we run with two identical, we have access granted. That's going to be the target for our demo. We want to see if we are able, by using some sort of injection, to force that function here, even though it's running with two different signatures, to print an access granted anyway. Can we disturb the call here enough so that the security measure of the signature comparison is completely bypassed? This is our target. Okay, and we're going to set that up in ES Reverse. So the primary interface of ES Reverse is in the form of a Python API called ES Firmware, and that's why the notebook here is a prime way to demonstrate that. And so we're going to load some form of emulation. There are multiple ways to do emulation. Here we're not going to get into too much detail. We just want to see the workflow. So I'm going to set up the emulation of that firmware, starting at the compare binding v1, and it's going to stop at printf because it's going to make it easy for me to see which path I have taken there. It's going to make it very visual. And we can run that emulation as we did before, but this time using ES Firmware, either with two different signatures, in which case we have access denied, or two similar signatures in order we have to have access granted. Again, now we have this the setup done, and we can start trying to run a fault injection campaign against that particular execution. Can we force that to print access granted, even though the signatures are different? Okay, so the fault injection is the purpose of that third notebook here. We're going to inject faults against an emulation of the function where we have two different signatures. Obviously, we are trying to see if we can twist the execution of that security measure into returning access granted, even though the signatures are different. So that's the emulation that we set up. But now, to inject faults, we need a fault model. We need to specify how we want to fault that process. ES Reverse's tools for that work at the level of the assembly code, so the compile code. We don't work at the source code level, we don't work at the microcode level, instead we work at the compile code and what's executed by the CPU, functionally speaking. That means that we can look at a disassembly of the function and see the registers and see how the code behaves there, and use that information to try and think about the fault model that we're going to have. So if we look at the compare binding function, which calls compare signatures, we can take a look at what's going on. Here we have the C version of the assembly code. So this is not the source code level, it's a decompiled version from the assembly. And we see that it calls compare signatures, which is this line. And then the return value of that, called res here, is actually stored in R0, as you can see here. That's because in the usual ARM calling conventions, the return value of a function is stored in R0. So obviously, even if the compare signatures returns, hey, this is these two signatures are different. If we change that, twist that, and force it to return, yes, the signatures are identical, then we will going to take the path of access granted. Okay, so that's why R0 is such an obvious first target for any fault injection campaign. Okay, so that's what we're going to do here. We're going to target R0 there and generate faults there on that run here. So let's do that. So even though I targeted the function, I don't know exactly where I should make that particular injection. Okay, so that's why the ES Reverse is going to do that for me. Inject fault everywhere possible, and we're going to see the results. So the campaign here is done. and we can look at the results. And most of the fault injection didn't significantly change the execution of the function. This is to be expected. However, we managed to find multiple places where injecting R0 and forcing it to a certain value did change significantly the result of that, and we managed to circumvent the security feature. So that's expected when we look at the code. However, it's very good that we can now verify that for real using ES reverse. And we can check, so we have 4 instructions, 4 places in time where the injection works, and we can filter the results there. For instance, look at the access granted. And the first instruction where that injection worked was 5674, and that's exactly the instruction that we were looking at. No, that's actually inside compare signature, I think. Let me see. Yeah, that's here. So here is where we copy the result into R0. Sig1 is also R0, as you can see here. So that's the return value. And this is where we copy the return value from within the function. So from that point on, starting at 74, if we start changing R0, then we will effectively modify the return value of the function. Yeah. So we have 74, 78, probably 7C, and yeah, and further. Okay, so that makes a lot of sense, but we are able to check what's going on there. Okay, now we've successfully asserted that our code contains a vulnerability against certain types of fault injection. So that was great, but now the fun begins because we can leverage that information and try to implement a mitigation against that. We are in this loop here that we saw before, where the developer gains some information and can loop back to its source code and try to implement something, try to make things better. Okay, so to do that, we need to look back to our source code. We have compare binding v1. This was our function, and we're going to make a new version of that function that successfully protects against what we saw. This is the v2 function, where instead of calling compare signature once, we're going to call it twice. This is a very simple mitigation that we're implementing here. And the reason it works is because we inject a fault that may disturb the execution of the first call, but then the second one isn't going to be disturbed. And so if one of these two returns an OK, not OK, that's enough to trigger the access denied path. This is possible because we are, for this demo, looking at a single fault model where we are only allowed one fault during the entirety of the execution. ES reverse can implement multiple faults, but this is not what we're looking at. Looking at single fault, so even if we manage to change the execution of the first call, the second one is going to be undisturbed, and so return an OK, and so we can take access denied path. Okay, so this is fairly simple mitigation. We implemented it as a developer, and now we can again run the same campaign and verify that it, successfully protects against that fault. Okay, so let's check that. We would be able to run that in CI/CD or something. So same emulation as before, instead that this time we are looking at compare binding v2. We start with an access denied, and we can check that it successfully prevents any access granted to be actually printed. Except that it doesn't. We have the exact same result as before. We have 2% of the injected fault managed to result in an access granted. And this is not expected. What's going on? In order to understand what's going on, we need to move back from the source code and return to the compiled version of the function. And if we look at it, compare binding v2, this is our function here, and we see that we have only one call to compare signature. We can verify that in the C decompiled version. Again, this is not the source code. This is really the C version of the function based on the assembly, based on what's actually compiled. And we see we have a single call to compare signatures. That explains why injecting a fault against R0 still manages to result in a access granted, because this is not significantly different from the compare binding v1. But what's going on? Why didn't we have 2 calls as expected? Well, the reason is that because, again, injecting a fault is something that is completely outside of the model of both the developer and the compiler. And so from the compiler point of view, there's no reason why these 2 calls should result in anything different. We're calling them with the exact same parameters. These 2 functions are constant. And so calling them twice is completely useless. So the optimizer will see that and just remove one of the calls and, take only the second one or the first one. And effectively, it will cancel the mitigation that we try to apply. And so our code is still vulnerable. And this is really interesting because if you implement code review, as is very usual in developing environments, a code reviewer might simply think that this is good enough and validate the code review and never look at the compiled code in the end. Or maybe this is correct once and then the compile optimization options change later down the line. Or maybe some conditions change that in one place allow that mitigation to work, and then later on it will not work even if you don't change the code. So many reasons where this might fail and not be caught by the developers themselves. That's why it's so important to validate your mitigation in a real scenario, and the emulation that ES Reverse provides of these fault injection campaigns really allow you to do that in a very, very simple and effective manner. So we know that this doesn't work. We can now again loop back. The developer has some new information, and we can go back to compare v3, a third version of our function, second version of our mitigation, where we ask the compiler not to optimize anything in that function. And is it going to work this time? So we run again our same campaign, but this time on compare binding v3, and we successfully manage to not get access granted, to keep the access denied, because the 2 arrays are different, and no injection against R0 is enough to disturb that function and circumvent that security measure. So that is something that is that we can verify for real here. And if we look again at Ghidra and at the assembly version, we see that we managed to get those 2 calls. And so even if one of the R0 is changed, the second one won't be. So we successfully take the access denied path. So that was really interesting because we see why it's so important to give access to the developers and or to the analyst, a simple way of running campaigns at this level, because there are so many things that can happen between the source code and the assembly code that we need to be able to check for real that our mitigations are effective. So what we've seen so far is using ES Reverse, we were able to target a firmware, a function, run a fault injection campaign on top of that, saw the vulnerability, implement a mitigation, and verify whether or not this mitigation was effective. And in our case, of course, it wasn't, so we were able to correct that. So that's good. But what if we move away from that slightly simple example? ES Reverse provides you with ways to run real-world fault injection campaign. And the first thing we need to talk about is the fault model. Just running R0 and checking if we set it to 0 is not enough, obviously. And we provide multiple fault models, multiple ways to enhance that thing and make it way more comprehensive. For instance, you might want to skip instructions, which is a very common thing to do. You might want to set registers to 0 or other registers or to other values. You might want to set masks, flip bits, and all the things you can configure within ES Reverse. And so you will get a much more complex, much more comprehensive fault injection campaign that you can run against your firmware and check for more types of faults and make your firmware way more robust to real-world attacks. So that's one thing. Also, it might not be trivial for you to find the function that you need to target. We saw that it was compare signature, but that might not be easy to see what your firmware is doing when it's booting, for instance, and you don't know exactly because maybe you're not super familiar with that part of the code. Or maybe a fault that you injected had a weird behavior. You're not sure how the fault leads, how the injected error leads to the actual behavior that you're seeing. The connection between the two isn't super easy. So you might use GDB on the firmware to look at what's going on. But also we provide a tool to do timeless analysis, to record a trace of the execution, for instance, of your fault, and then after the fact allows you to look at this trace and make connections and understand what's going on in a way that is way more user-friendly than just using a GDB. So this is what we're going to take a look for a minute here. So what we're looking at here is a recorded trace of the execution of our firmware in a different part here. We are looking at the main loop, so we are past the signature comparison in this case, but it's just for an example. So what we're looking at here in the middle is actually the trace of execution. It's not the list of instructions of the binary that like you would get in a disassembler, but this time it's a view of time. So if I have a branch here, a call, the next instruction is going to be the destination of that branch. Yeah. And really, effectively, this is the axis of time, and I'm moving forward in time doing that. And if I move up, I'm moving backwards in time. And at each of these points, I have access to the same information I would have in a debugger. I have this view of the CPU. I have also the backtrace there. I can access any piece of memory that I want to read. So this is very similar to what you get, but you don't have to worry about skipping a point and having to re-execute everything from the beginning to move backward. You have access to the entire trace, and it's fairly easy for you to seek in your trace forward or backward and see what's going on. And you see that you have quite a few niceties there to help you get an idea of what's going on. You get a view of the strings being manipulated in your trace. And very importantly, you get what we call the call tree, which is a view of all the calls made represented as a tree. So for instance, here, offset nameLen made a call to this function and then quite a few others. It's probably looping somehow, and you can also move backwards, and you can look at the parent and again fold. So it allows you to get a better idea of the behavior of a function, and maybe you will see in this call tree that one function shouldn't have been called, and maybe that's a clue to what's going on. So yeah, that's using this tool gives you a very powerful way to analyze the behavior of the execution of a piece of code, and either understand what the fault is doing, or understand the type of function that you should probably target in your fault analysis campaign. Okay, so that's it for this demo. I hope you learned something interesting about how you can use ES-Reverse to launch fault injection campaigns on firmware and do some analysis with the information that you get in order to make your software more secure.
Okay, thank you, Mathieu, for recording this. I hope you have a good vacation. I see a raised hand. We have time now for answering questions, and I will check in the chat if there are questions that we need to answer.
Hello?
Yes, I can hear you.
Yeah. Okay. Very interesting presentation. Thank you. I have one question. So you are presenting that it is possible to do on firmware level. Is it some possibilities to do on microcontroller level? So some kind of technique to simulate one type of family of microcontroller?
Yes, it's Guillaume Vinet speaking. Yes, indeed, we support different type of emulation to support different microcontrollers. So currently you can either emulate Linus Elf executable. After that, we can just emulate a piece of code. You select your CPU, you create a memory, you put a memory inside, and you can emulate it. And the last one is that we will support QEMU board. So every board which is supported by QEMU, we will be able to emulate them and to fault them. And also we will add a possibility to customize the behavior of the board. Does it answer to your question?
Okay, yeah, thank you.
Okay, so yes, I was wondering if it was possible to use this tool instead of using an emulator, to use it through a real debugger like GDB.
Yes, indeed, the emulation is compatible with GDB. For the fault injection part, we have an automatic engine. And once you have obtained an interesting fault, you can just emulate the fault, and you can connect GDB on it to make more investigations.
Okay, so but the testing must be done on the simulator.
Yeah. Currently, we doing emulation. Yeah.
Okay.
Okay, thank you, Guillaume, for answering this question. And then I would like to end this webinar by stating that, of course, if you are interested in our solution, then please contact us. My email address is jan.jager@eshart.com, but you can also visit our website to get some more information. And please reach out if you have any questions. We are happy to answer all questions. And of course, there are always possibilities to do a demo specifically for you, or we can also organize a trial with our EOS Reverse platform. So thank you for attending this webinar, and I would love to see you again, maybe for a demo or a trial. Thank you.